All right, what's up, everybody? So let me turn this down just a little bit. They're not clipping. Welcome to our latest review, Chapter 31. I've gone ahead and called this chapter Electrical Engineering. We're going to cover a whole bunch of different types of circuits in here. The reason I'm calling it Electrical Engineering is because basically we're going to be doing electrical engineering in here. This is going to be the hardest chapter of the entire semester. This is the last chapter before the second exam, and then of course we'll hit another reset before going into the final stretch of physics. So yeah, this is going to be the I think it's the most difficult chapter in this course. So I call it electrical engineering to make a point here, which is that there should be two groups of people at this point in the course. People who are going to go into electrical engineering, in which case you will cover this stuff for the rest of your education, and it's okay if you don't get it quite yet. The other group of people is people who are still taking physics because they need to finish physics for some other engineering degree or some other degree, in which case you're not going to be doing a ton of electrical engineering going forward. And for that group of people, it's okay if you do not fully understand this. So I think most people, as we go through, maybe you'll be understanding half of the problems. Maybe that means you get 4 out of 8 of them, or maybe that means you only understand half of each problem. That's fine. The good news is there's no quiz on this. This is the last chapter for the second exam, and then it will be, maybe a question or two. And if you, manage to get one of those 2 questions or something like that on the exam, then you're in good shape, but you do not have to take the quiz. So we're just going to focus on getting through these 8 problems. Now there's quite a bit of theory that I could go into, and I am going to take this opportunity to review basically everything that we've done with circuits, or I should say, crucially, the 3 different components that we've encountered. So capacitors, resistors, and now we have inductors. And we know from when we did capacitors and resistors that you can plug capacitors and resistors into each other and form RC circuits. Now that we have inductors, we can form CL or RL circuits as well. So we can plug a capacitor into an inductor and a resistor into an inductor, and different things are going to happen. So first of all, let's go ahead and review capacitors, resistors, and inductors each on their own and talk about how they behave within a circuit. So I'm just going to make a little chart here. In the order that we encountered them in this course, we have capacitors, resistors, and inductors. And with capacitors, we talked about the energy stored in a capacitor. We had a few different equations for it. But basically, remember that the idea with a capacitor is that you have energy that is stored in the electric field between the parallel plates of the capacitor. And that energy, we'll go ahead and use the equation. I think the only one we're going to use today is 1/2 CV squared. And then for resistors, if you recall, resistors don't store energy. Remember, resistors actually remove energy from the circuit. So resistors emit a power. You can think of a light bulb as a kind of resistor. Also, all wires will have some resistance in them. So we don't exactly talk about energy. We talk about the rate of change of energy. So I'm going to put it in a little bit of a different color so we don't get too carried away here. But this would be the equivalent calculation that we might be asked to do with the resistor, which is to find the I squared R for the resistor. Now inductors, I covered this a little bit last week, but I'll just go ahead and state it authoritatively right now, that inductors also store energy. Unlike a capacitor where the energy is stored in the electric field, inductors store energy in the magnetic field. And that was all that Faraday's law with the Lenz's law, and how when you have a magnetic field through a loop of wire and that magnetic field changes, there's an induced magnetic field. All of that was just to describe how inductance works. And so that magnetic field through an inductor is going to store energy in the inductor. And the equation that we're going to use when we do need to calculate that is to do 1/2 Li squared, where L is the inductance and I is just the current through the inductor. Because remember, the magnetic field present inside of an inductor is dependent on the current running through the inductor. All right, so all of that being said, make sure the sound is, hoping the sound is good. Using a different mic setup. I want to make sure that I'm not clipping too hard. Okay, so we have our energy considerations. We also have considerations for the voltage through each of these. And this is where the sort of lineup of capacitor, resistor, inductor is really clearly emphasized. The voltage in a capacitor was 1/C times Q. It was Q over C, but I'm going to write it this way for a specific reason, just to say the coefficient is 1/C, and then Q is the charge. The voltage over the resistor was I times R. I'm going to write it this way, R times I. The reason I'm writing it this way is just to emphasize that we had a coefficient times charge. Now we have a coefficient times current, which is the rate of change of charge. And then for the inductor, the voltage is going to be L times di dt. So di dt is the derivative, the time derivative of the current. And since the current was the time derivative of the charge, that means that di dt is going to be the second derivative of the charge with respect to time. So we're going to put these little labels here. This is V sub C, this is V sub R, and this is V sub L. Now, I could define this at some other point, but I'm just going to go ahead and do this right now. And I don't think I'm going to go through too much of a derivation here. Well, let's see, our first problem, yeah, we're going to have to go ahead and tackle an LC with the first problem. Let's go ahead and talk about the different types of combinations that we can have when we plug all of these guys in, and the way that these components interact with one another when they're in a circuit or just an arrangement. So we'll come back to this chart, but let's make a second one here for the three different combinations. So the three different types that we have. We've already covered RC circuits, and we've covered LR circuits. We covered those last week, I believe, just a little bit. We'll talk about them again. The last one that we can do is we can plug in an L and a C into each other. Now this isn't actually going to be a circuit because there's going to be no battery. So what I'm going to do here is make a sort of a note. Maybe I'll do sort of two lines. We're going to compare them all here. But what I just want to mention here is that we have no, I'll go ahead and use epsilon for EMF to get used to that notation. The electromotive force is another way of saying the battery. So we have no EMF for the LC circuit. But first, let's just talk about RC and LR and how these work. In both cases, the first thing that we want to talk about is the limits. So when, oops, let's see if I can get it. Let's see, when time, running too close to the side of the screen here, from time is equal, it's not going to work for me. So from t equals 0, okay, when time is equal to 0, when we have an RC circuit, remember, you close a switch and you have a resistor and a capacitor connected in series. Remember what happens is that initially there's no charge on the capacitor. It takes time for the charge to build up on the capacitor because current has to flow through the resistor onto the capacitor. So initially, the entire battery, which we're calling now the EMF, is all going to be stored up on the resistor. So the voltage of the resistor is equal to EMF is equal to the voltage of the resistor. And initially there's no charge stored in the capacitor, so the voltage of the capacitor is 0. After some time, which we'll say t goes to infinity for lack of a better notation, but just much longer later, once the charge is allowed to store up in the capacitor, in other words, once you have charge stored up in the capacitor, now there's no more current flowing because the capacitor is fully charged. So it's as if the resistor isn't doing anything anymore. And so now your EMF is fully stored up on the capacitor, and now the voltage over the resistor is going to be equal to 0. All right, in the same time frames for an LR circuit, what's going to happen? This is going to be actually a little bit different. So I'll go ahead and copy over these labels, t equals 0, and as t goes to infinity. When I close my switch and I have an inductor connected directly to a resistor, what's going to happen? Remember, the inductor here is the thing that limits the change. So the inductor does not want current to flow through it initially. It resists the flow of the current. Why? Because there's no magnetic field and it doesn't want magnetic field. It needs to get used to that idea. Remember, the inductor hates change. So initially it's actually the inductor in this case that's using up all the EMF by resisting the flow of the current through it. So the EMF is entirely on the inductor. And so since the inductor is not allowing any current to flow, that means that the voltage through the resistor is equal to 0 because the voltage of the resistor requires current to flow. Now, eventually the inductor will get used to the idea of a current flowing. It will allow current to flow through it. And then at a certain point, it's no longer contributing anything. Once it's fully adjusted, it's as if that coil of wire is a straight wire. So it's no longer even functioning like an inductor, really. And so all that we have, other than the fact that there would be energy stored in it that could be released, which we'll take a look at in a second. But so long as we've closed the switch and are allowing the circuit to do its thing, now the EMF will just be fully through the resistor, and now the voltage through the inductor is going to be equal to 0. All right, so there's quite a bit of theory there on how that works, but here's at least a chart that you're allowed to take with you, put in your notes for now. And these are your end behaviors. Remember, in between time equals 0 and as time goes to infinity, we have an exponential function, the e to the minus t over tau, with some constant out front. And the tau is different for RC versus LR. We're not going to talk about that this week, but if you'd like to put this on a sheet for reviewing later, you could also have a row in between these two that has sort of an intermediate. So maybe make a note of that for later as you're studying for the exam. Cool. So the last thing then is to talk about an LC oscillator. Now, as I mentioned, and I wanted to just reiterate, there is no EMF here. There's no battery in an LC operator. Typically what we have is we have like a capacitor that is charged up initially. So we'll have a bunch of charge in a capacitor, and then we attach it to an inductor. And what's going to happen when we do this is that you have some energy on your capacitor that's stored up in the form of charge. That capacitor is going to release the energy. So the charge will start to trickle off of the capacitor, and it would like to just flow through the circuit. However, there's an inductor on the other side that does not want the current to flow through it. The inductor hates change. So what happens is it takes some time for the charge to trickle off of the capacitor through the inductor, because the inductor has to get used to the idea of current flowing. And this is why we call this an oscillator, because the energy in the capacitor that is related to the charge stored there is slowly transferred into energy in the inductor that is related to the current that is flowing through it. Then the current flows through the inductor to the other plate of the capacitor and stores back up on the capacitor as charge, and thus you have energy transferred back to the capacitor. And then the energy wants to leak back off again, so the energy is going to leak back to the inductor, and then the inductor resists the current flowing through it, but eventually the current will flow through, and the charge is allowed to build back up on the other plate of the capacitor. This is one full cycle. One full cycle means that the polarity of the capacitor goes from positive over negative to negative over positive, then back to positive over negative. You won't necessarily need to know that, but the most important thing here is to recognize that we have oscillations. Oscillations mathematically are described with a trigonometric function, right? A sine or a cosine wave. And we also are most importantly in this section going to describe these oscillations in terms of a frequency or a period. So we're going to have a base level frequency that I'm going to give you the definition for here. But from Physics 1, we have some ways of tying frequency into period, and I'll talk about those. I'll go ahead and write that down here as well. But the one thing that I really want to emphasize here is that the frequency of an LC circuit is going to be 1, or LC oscillator, I should say, is going to be 1 over the square root of L times C. So it just depends on what your inductance is and what your capacitance is. That tells you the frequency with which the energy is going to pass back and forth from one to the other. But again, just to emphasize, it's going to be energy that's passed here. I'm going to go ahead and put right below this, just as a reminder of how we can relate frequency to period. Just as a reminder, that frequency is equal to 2 pi over the period. We're going to need that to solve some problems this week, but that is not foundational. The big foundational thing here is my definition for the frequency. Ultimately, we're going to plug a resistor into this in a little bit, but I think for right now, we have enough to at least tackle a couple problems. So we will, I think I want to cover one more, before we jump into the problem, I want to cover one more slide of theory and some equations. So we're going to go back to, I'm going to sort of relate this back to the last slide that we were on. Oops, too big. All right, so I talked about these 3 different voltages, and I made a point of relating charge to the rate of change of charge to the rate of change of the rate of change of charge. And what I want to do now is, now that we know that there's a frequency of oscillation that is related to these LC circuits, I just want to mention that we can express both of them in terms of current. So this is going to be a little funky as far as what I'm doing with the notation here, but basically we can rewrite our voltage of the capacitor as 1 over C times the integral of I dt. So we have current, that is sort of our baseline, and we're going to have an integral of the current on one side, and we'll have the derivative of the current on the other side. Okay, we just want to form this mathematical formulation. What we ultimately want to get at here is we want to have a way of describing the maximum voltages for each of these. Now, our current in an LC oscillator, and in a second we'll have a RLC oscillator, but our current in the LC oscillator, as I mentioned, it's cyclical. So that means that it is described with a sine or cosine wave. And just as a reminder, a sine or cosine wave will have, say, if I wanted to do an I of t is equal to, it depends on which one's stored up. Generally, if your capacitor is stored first, then you just start with like a I cosine of omega t. We'll just do this. We could get a little more technical with our mathematical definition, but we have all the pieces here that we need. So we have an amplitude that is big I, is the amplitude of the current, that's your maximum current. And then we have a cosine function that varies with time. And omega right here is that omega that we just defined. That's our frequency of our oscillations. So what this means is, to go back to this last slide, I need to know what happens when I have an integral of I dt, and I also need to know what happens when I take a derivative of I of t. And we can actually do each of those with this equation right here. The integral of I of t dt, I'm not going to have a plus c. I'm doing an indefinite integral. I'm waving my hands a little bit here. But the point is that when I integrate this, I'm going to get a cosine, and I will also, via the chain rule, end up with a 1 over omega that'll come out front. So I have big I over omega, and then I have a sine of omega t. And then I can also do a derivative. Let's use a little bit of different color here. A di dt, or an I prime of t. And with this one, we'll have the derivative will be negative sine, and then by the chain rule, we'll pick up an omega out front as well. This omega will be in the numerator. So I'll have negative omega I sine of omega t. Okay, now with these, what we can do is we can go back and we can define now all of our voltages in terms of these functions. So this one right here, this top one, will go into the V equals IR, the voltage of the resistor. The blue function here will go into the V equals L di dt, the voltage of the inductor. And this other one over on the left-hand side will go into the capacitor voltage. So you have 1 over Q times this whole function, and that will give you the voltage over the capacitor. Now, what I have just described there are some pretty complicated equations. In this section, you'll use those complicated equations at some point in your life, and we will talk a little bit about the different phases between these, because you'll notice they're not all lined up. They're 90 degrees off. We'll talk about that toward the end of the chapter. But what I'll just mention is that for this chapter specifically, we are only going to be concerned with the amplitudes of the voltages. So what that means is, to go back here, hopefully you still have some room in your notes, but to go back here, what we're going to end up with is our maximum voltages for each of these. And so we'll have, say, a V sub C max. When we put our 1 over C in conjunction with the stuff that we had before, we'll have 1 over omega C times big I, where big I, remember, is the amplitude of the current. For the resistance, V sub R max this is just going to be what we already had, R times big I now. And then for the voltage over the inductor, our V sub L max, we're going to have omega L times I. Why did I want to do this? Because I want to describe all of these in terms of the current, and we're just going to do it in terms of the current amplitude, which is very nice. You'll also notice that we now have coefficients that include both the capacitance and the inductance, and that omega that talks about the frequency of oscillations. So one way that we're going to see these all written is we're going to see it in terms of the, we're going to start to call these guys here the reactances. All that word reactance means, if you've seen that this week and you're wondering what it means, the word reactance just means the equivalent of resistance for capacitance and inductance. So we just call those reactants instead of calling them resistance. You could call it like a capacitor resistance and an inductor resistance or something, but they just call it a reactance to make sure we're not claiming that it is a resistance. But I will say that those terms that are boxed in yellow do have units of resistance, so they do have units of ohms. And generally we will call them, I'm out of room a little bit here on the left-hand side, but if you wanted to write this as just one term as reactance, this would be X sub L. So you have X sub L times I, and then for the other yellow term here, I'm sort of out of room, but that will be an X sub C. But it's important to just know what those are actually equivalent to. So we have 1 over omega C for the reactance for the capacitor, and omega times L for the reactance of the inductor. All right, so that's a lot of theory. Let's go ahead and jump into some problems. We sort of needed to go over all of that before we jumped into these problems. Yeah, was that 20 minutes or so? All right, that's not horrible. All right, so problem number 1. We have a capacitor. It looks like a circuit. It looks like we're going to have resistance and capacitance and inductance, but because of where the switch is, we're never going to have all three of them interacting at the same time. So what we do is we first of all switch it to position A. When we switch the switch to position A, you'll notice that the inductor is cut off because the inductor is on the bottom. So when we're in position A, we just have a simple RC circuit. And we're going to keep it at A for a very long time, which means we're actually going to go right to the very long time case for the RC circuit, which is this box down here. And we know after a very long time, the EMF of the battery will be all over the capacitor, and we know the voltage of the resistor will be 0. So for part A, we know that the EMF of the battery will be voltage on the capacitor, and we know that the voltage over the resistor is equal to 0. And then we simply go to work here. The first thing they ask us to do is to find the frequency. What is our frequency? Well, we know the angular frequency is omega equals 1 over the square root of LC. And they're, I guess because they don't say angular frequency, they want you to intuit that what they actually want you to calculate is the linear frequency f. That linear frequency, of course, is omega over 2 pi. This is just from physics 1, so maybe it's not an of course, but just a reminder that that's from physics 1. So part A, you just need to know L and C, and those are actually given explicitly to you, so you can just go ahead and plug those in right there. And this is when we throw it into position B, by the way. Once we throw the switch into position B, I should mention now the resistor is removed, and you just have whatever voltage was stored in the capacitor and the corresponding energy. That is now going to be passed back and forth between the capacitor and the inductor. So when we're in position B, I need to mention we have an LC oscillator. That's what we're calculating right here, is the frequency of the LC oscillator. In part B, they ask us to find the current amplitude of the LC oscillator. Well, I know that the voltage over the capacitor is going to be equal to the EMF because we stored that when we were plugged into the resistor. And I know from what we just wrote down on just that very last slide that the voltage over the capacitor is equal to, what was it? Sorry, 1 over omega C times I. So in this problem specifically, they're asking you to find I. I know that my EMF is stored fully on the capacitor, so I can just plug in whatever EMF they give me. And then I've found omega in part 1 sort of along the way. and I am given the capacitance as well. So new equations that we have to use, but we know how to use them, and the actual calculations here are not too bad. We will get into some pretty wonky problems in a little bit, but I think the first 2 or 3 are just sort of straightforward 1 or 2 piece calculations. All right, part 2, yeah, we have another oscillating LC circuit, and they give us an amplitude for the current. So they go ahead and give us that big I. So let's go ahead and list out our givens. We're going to be given a bunch of stuff and asked to calculate a bunch of stuff. So give us the current amplitude, that's big I. They give us the potential amplitude. What is our potential amplitude? We can think of that as like our EMF, or actually let's go ahead and call that a V max, because we've called that V max in our notes a second ago. And we're given the capacitance as well. Notice what I do not have here in an LC circuit, I do not have the L. I will maybe be asked to find that at some point. I will certainly need to find it at some point. I also do not have the frequency just yet, but I do know a way to relate these 3 together to find the frequency. In fact, I just used it right here. This equation that we used in part B on question 1 has the voltage, the maximum voltage of the capacitor, as it relates to the frequency, the capacitance, and the current. So you could go ahead and find the frequency right away with this equation. They ask us to find the period in part A. Well, I mentioned this again somewhere in our notes, the relationship between frequency and period. Oh, my face is covering it. There we go. Relationship between frequency and period right there. Once you find the frequency with the V max for the capacitance equation that I circled a second ago, you can use it with this equation and go ahead and solve for that period. You just do 2 pi over whatever you find with this yellow equation right here. All right, and next part B, we want the maximum energy stored on the capacitor. Well, I know that the equation for the energy stored in a capacitor is 1/2 CV squared. If I want the maximum energy, then I need to plug in the maximum voltage. That's already given, so that's just a 1 and done. Part C, they ask for the maximum energy stored on the inductor. If you recall, I mentioned that in an LC circuit, in an LC oscillator, LC circuit, LC oscillator, what's going to happen is the energy is going to be passed back and forth. So if I have 10 joules on the capacitor at one instant, then sometime later it'll be 10 joules on the inductor, and then that 10 joules will go back to the capacitor, and then back to the inductor, and then back to the capacitor. So they're just going to pass that same whatever amount of energy back and forth. So the maximum energy on the capacitor is the maximum energy on the inductor. And in fact, if you want to derive the definition right here for the frequency, you can just set 1/2 CV squared equal to 1/2 Li squared and solve, and that's actually where that definition for the frequency comes from. So same energies on both, same maximum energies for both, I should say. Only one would be at a maximum at a time. It's like a pendulum in that sense. D, they ask for the maximum rate at which the current changes. So for the maximum rate at which the current changes, we only have one equation that includes the rate at which the current changes. And that is the voltage of the inductor. So this is for part D. The voltage of the inductor is equal to L di dt. If I want the maximum of di dt, then I'm going to need to have a maximum voltage on the inductor. So we have the Vmax right here. You can go ahead and plug that in. The only thing you'll need to do is a little bit of legwork to find the inductance, because we haven't found it yet. But we did find our frequency in step 1. So once we find in step A, I should say. So in part A, we found a frequency, and we know that that frequency is equal to 1 over the square root of LC. We know the capacitance. We take the frequency that we found on our way to finding the period and solve for L. And then you can plug L into this equation right here. The last part does take a little bit of work. This is a little bit of a more difficult calculation. They ask for the maximum rate at which the inductor gains energy. So I want the rate of change of the inductor energy, which is a little funky. I know that the inductor energy is 1/2 Li squared, but they want the rate of change of the inductor energy, right? So that would be du sub L dt. Now, du sub L dt is going to give me a chain rule here because my current varies with time. Since this is an LC oscillator, I know that current is going to have the, I cosine omega t. We did this when I was sort of giving the notes here. It's equal to big I times cosine of omega t. I'm just going to write cosine omega t. And so when I differentiate, I'm going to have a chain rule. So I'll have a 2 that comes out in front and cancels out my 1/2. So I have Li, and then I also have a times a di dt. And di dt from this formulation, we already did this when we were doing the notes, but just as a reminder, di dt is going to be negative I omega times times sine of omega t. So plugging in for I and di dt, this whole thing is now going to be equal to L times I cosine omega t times negative I omega sine omega t. That negative sign will come out in front. That's really just going to tell us about the phase shift. But we can pull out our i's and our omega and our L, and we can pull out the negative sign as well. And we'll have negative I squared L omega, and then cosine omega t sine omega t. How do I combine sine omega t and cosine omega t together? This is a trig identity. That'll be equal to 1/2 sine 2 omega t. So putting those together, combining them together, we'll end up with another 1/2 times sine 2 omega t. So I can go ahead and pull that 1/2 out in front as well. I've got a negative sign out there as well. What I'm ultimately after here, of course, is the maximum of this function. The maximum of the function is just going to be whatever the coefficient is, on our final sine function. And so what we'll end up finally having is negative 1/2 I squared, come on, let me get an I in there, I squared L omega times sine 2 omega t. As I mentioned, the only thing we need here is just the coefficient on the sine function. That coefficient is just going to be this stuff right here. The negative, we can go ahead and ignore it because you'd hit a positive amplitude and a negative amplitude alternately. But you have everything from previous parts of this problem to go ahead and solve for that. And yeah, that's a little bit of a difficult one. I'm not sure that there's a lot to take away from it because you do have to do like a trig identity. But the lesson there is that there is something important about the fact that there's a phase difference between like your I of t and your di dt. And we are not going to hit that phase difference just yet, but we will need to talk about that in a few more problems. So we have a little bit more theory. All right, let's do problem number 3, or talk about problem number 3. Problem number 3, we're going to finally plug a resistor into an LC circuit. Let's talk about what happens when we do. We haven't talked about that yet. So the LC oscillator, we talked about, the energy just goes back and forth from the L to the C, and they'll just pass it back and forth forever. The corollary to this from Physics 1 that some people may remember, maybe not, but in Physics 1 we talked about specifically a car with a suspension, and the car would hit a bump, and the suspension has springs, and those springs would bounce, and you do not want those springs to bounce forever. In a car, you're just going to bounce up and down until the end of time. So in a car, what you do is you also include a strut or something to remove that energy from the oscillation of the suspension. And that is, we called it a damping, I think we just did like damping coefficient in physics 1. It would give you a damping force. Well, in physics 2, the thing that we can use to remove the energy from an LC oscillator is the resistor. So in this problem specifically, we're going to plug in a resistor, and we want the oscillations to decrease. And we're going to do it kind of in a similar way as to how we did it in physics 1, which is to define this whole long big thing for the charge, where we know the charge is going to have a cosine omega t, and we know that there would be some amplitude q. We know this would be a function for q of t. So this is sort of what we had already, right? Where we had I of t is equal to I cosine omega t. And since we want to dampen the amplitude, we need to include a term in here. And this is what we did in physics 1. We include a term in there that's e to the negative RT over 2L. This is actually, I think, very similar to what we had in physics 1. And the only thing that we really did with this in physics 1 is we said this right here represents the amplitude as a function of time. So instead of having a wave, a cosine wave that just goes up and down forever, instead we have a cosine wave that has decreasing amplitude like this. And so this function describes just the shape of the amplitude as time increases, and that will have an exponential decay. So the equation that you're actually going to use in this problem is you'll use that function for Q max in terms of t. That'll be equal to Q times e to the minus RT over 2L. That's the only thing that you need to worry about. Remember, in this chapter, we're mostly going to constrict ourselves to looking at magnitudes. And so here again, we have a magnitude. We just have a function for the magnitude with respect to time. All right, and then in the problem, they give you a number of cycles. That number of cycles is a number of periods. So your time here, you would plug in terms of the number of cycles times the period. So if it's like 50 cycles, then you'd have t is equal to 50 periods. And then ultimately, you want to replace periods with 2 pi over omega. So you'd have 50 times 2 pi over omega. And we know how to calculate omega already. That's just 1 over square root of L times C. So you use that same equation that we've used so far. Okay, so that's going to be your time. And then, yeah, and then they also tell you that you want to decrease the amplitude or decrease the maximum charge to some percentage of its initial value. So that means that what you'll do is you'll replace Q max of t. If they say 90% of the initial value, you'll do 0.90 times Q on the left-hand side, and on the right-hand side, you'll have Q times e to the minus R times this junk right here over 2L. And then you can cancel out the big Q, and you can go ahead and solve for whatever they're asking you to solve for, which in this case I believe is the resistance itself. So we're going to solve for big R, and I'll leave that execution up to you. That's just a one-part problem. And then in problem number 4, we introduce a concept, another new concept. This is the concept of an AC generator. So far, all of the batteries that we've had, all of our EMFs have been direct current, which means you just have a positive terminal and a negative terminal. It's just a battery, like a AAA battery or AA battery. A lot of our electronics, some of you may not even be familiar with the static battery like that, but a lot of our electronics now operate according to an alternating current. So what happens with an alternating current is you have positive negative that switches to negative positive, that switches to positive negative. And the whole point is that instead of just having a voltage, is a battery where the voltage is equal to 10 volts and you plug it in, you have 10 volts in the circuit and that's it. An alternating current is going to flip back and forth, and so the voltage is described with a sine or cosine function. So that means it's going to have a frequency. And for this problem where we're calculating the amplitude of the current over a capacitor, we just have to use the equation that relates the maximum current over a capacitor to a voltage. So that's just this little equation down here, that the maximum voltage is equal to, 1 over omega c times the current. So this is for problem number 4. You have that the voltage of the capacitor maximum is equal to 1 over omega c, omega c times the maximum current. And I think they're going to give us, they give us the EMF, the E max, it's epsilon max right there in the problem. That's what you're going to plug in right here. And then they give you 2 different frequencies to try. Keep in mind that those are given in hertz, so those are linear frequencies f. So for omega, remember omega is 2 pi times a linear frequency. But you just take those frequencies that they give you, multiply by 2f, and plug them in right there. And I believe they're going to give us, they give us the capacitance as well. So they give you epsilon, they give you the capacitance. You can find omega pretty quickly. And then you just solve for the 2 different currents. In problem number 5, it's going to be, I think it's an identical problem. These 2 problems have been here the whole time I've taught this class. It's an identical problem, except now it's for an inductor. So we just need to use the maximum inductor voltage equation, which is omega L times I. We still use this same frequency equation here, but now we're going to plug in that for omega. They give you, again, a maximum EMF that goes in on the left-hand side, and they give you the inductance in millihenries. Make sure you convert to henries, and then you can solve for the current. Okay, now that we have AC oscillating voltage sources, AC generators, now we can tackle the big kahuna. And the big kahuna is an AC battery or an AC voltage source plugged into a resistor, inductor, capacitor circuit. All 3 of them plugged in together. Let's take a second to draw what that would look like. You have the symbol for an oscillating voltage source. It looks like this. We're going to plug this into an inductor, a resistor, and a capacitor. There's everything we've done in the whole semester, an entire semester's worth of work, and one fun RLC or LRC circuit. This is our EMF. And there you go, you're done. You did physics, you've done all of electrical engineering. Great. So there are going to be a few things we're going to be responsible for here. Now, one thing that I want to mention is for now that there are 2 frequencies involved now. There is what's called the driving frequency, which is the frequency of oscillations for the AC source. That's your driving frequency. And then there's what's called the natural frequency, which is the 1 over square root of LC that we've been doing throughout this chapter. Those are 2 different frequencies. When I'm playing around with an AC source connected to an LRC circuit, I'm playing around with the driving frequency. The frequency that I get from the inductor and the capacitor, the natural frequency, that doesn't change. That's just a fact of the nature of those 2 pieces of the circuit. So when I am calculating, or when I'm playing around with the circuit, I need to keep in mind that the only thing that I can change is the driving frequency. And this is what the graph that is in front of you is showing. You're changing the driving frequency, which means that there's probably a dial here that says, omega driving, and it has a little notch on it, and there's all these different values that you can hit, and you're just going to spin that, and as you do that, it'll cause the positive and negative terminals to switch faster or slower as you increase or decrease the dial. So that's why you have a graph there that has a frequency on the horizontal axis, and then you have a corresponding current on the vertical axis. The reason why the graph has that shape is because as your driving frequency gets closer to the natural frequency, the 1 over the square root of LC, as this frequency gets closer to that one, the current is actually going to increase until it hits its maximum when they're equal. And that is a condition called resonance. So resonance occurs when your driving frequency is set equal to 1 over the square root of LC. Two different frequencies, driving versus natural. When driving is equal to natural, you achieve resonance. And at resonance, your current is going to approach its maximum value. So that's how we can look at the graph that we have there and determine that the peak there corresponds to the maximum current. And also the frequency, if I read the graph, the frequency that I read off of there corresponds to the natural frequency. So in this problem, they're going to give me the inductance, but they do not give me the capacitance. So I need to read off the frequency that gives me a maximum current, and I can set that frequency equal to 1 over the square root of LC and solve for the capacitance that way. As far as finding the resistance, I'm going to get into why this is the case in just a second. But for right now, what I'll tell you is that at the maximum, when the current is at its maximum, or when we are in the case of resonance, what's going to happen is the inductor and the capacitor will cancel out. We'll talk about how they cancel out in just a second. But for now, it suffices to say that the inductor and capacitor essentially cancel each other out. And in that one instance, the only thing that is using voltage is the resistance. It's not exactly correct. We'll talk a little bit more about that in a second. But for right now, it suffices to say that at resonance, we have our driving frequency is equal to 1 over the square root of LC. Our current goes to its maximum. And the EMF of the battery, the maximum EMF, is used up entirely by the resistance. So our EMF of the battery, or what do we actually, yes, okay, so they give us the EMF amplitude. So the EMF of the battery will be equal to the big I, which is our amplitude of the current, times the resistance. And these are the three things that happen at this case of resonance. Now we start with resonance, but we will do a problem in just a second. Well, our last two problems, I think, are going to be in cases where we do not have resonance, and we have to talk a little bit more about the theory of how the inductor and the capacitor cancel out. But for right now, we do one resonance problem. On your exam, you're much more likely to have a resonance problem than a problem that's based on the next two problems. Having said that, I have seen exam problems based on these last two on the homework. So we're going to go ahead and tackle them. And I'm going to talk a little bit, yeah, we're going to have to do phase angles here, and I think we're going to have to do phase angle for both. Let me just double check what these problems look like. Oh, actually the last problem is also a resonance problem. Let me just take a look real quick. I think we can go ahead and talk about problem 8 as well. We might only need to talk about problem number 7 in terms of the interactions of the three different voltages. Let's see. We're given an RLC circuit. Can the amplitude of the voltage across the inductor? Okay, in order to answer that, we're going to have to look at a diagram here in a second. And then they're going to ask us, is there an RLC circuit with a driving EMF amplitude, a resistance and inductance and a capacitance? Find the amplitude of the voltage across the inductor at resonance. For the part B there, the voltage over the inductor will just be, you could do part B, but I guess, okay, we're going to go ahead and have to do the theory real quick. Get a sip of water here. Okay, so clear off some of these. Well, we're fine here. All right, so let's go back here. So we have these three different voltages for the capacitor, capacitor voltage is related to this function here. Resistor voltage is related to this function here. Inductor voltage is related to this function here. So far, we've been good to just investigate what goes on with the amplitudes, which are the terms out in front of the sine or the cosine. In order to properly solve RLC circuits, what we need to do is grapple with the fact that each of these is 90 degrees out of phase. What I mean by that is the capacitor voltage, which corresponds to this term right here, has a sine omega t shape. The resistor voltage, which corresponds to this one, has a cosine omega t shape. And the inductor voltage has a negative sine omega t shape. If I were to graph those together, just to get an idea of the shapes, my capacitor was a cosine, my capacitor had a sine omega t shape. So it would have a shape like this. That's one period. We'll go ahead and call that V sub C. My resistor had a cosine omega t shape, which has this shape like that. That's your resistor. And the inductor has a negative sine omega t shape. So negative sine omega t is going to do something like this. Okay. Now, this gives you an idea of how each of these is going to vary with time independently. And they will be positive or negative, and those will mean something. What this does not give us a clear picture of is the way that they're going to add together. And so what we can turn to is this tool, this mathematical tool that probably none of you have seen before, but it's a different way of visualizing oscillations. Instead of doing a function on a 2D plane like this, we can turn a sine or a cosine wave into a vector that just rotates around. There are a lot of different ways of explaining why this works. The one that always sticks in my brain is if you were to take a point on a wheel, next time you're looking at a car or a bicycle or something, pick a point, watch that point go around. As that point goes around, you could graph its position in the x and the y, and in the x and in the y it would have like a sine and a cosine function, but it's also rotating around with a given frequency. So that is what allows us to introduce this methodology that is called a phasor diagram. And so I'll go ahead and do it on the same page. What we will have is, since our inductor hits this negative maximum before the resistor and then later the capacitor, since it happens in that order, we say that the inductor leads by 90 degrees, then the resistor 90 degrees later, and then the capacitor 90 degrees after that. So inductor comes first, 90 degrees later is the resistor, 90 degrees later is the capacitor. In light of that, we will draw their vectors like this. This will be the voltage of the inductor. 90 degrees behind it will be the voltage of the resistor. 90 degrees behind that is the voltage of the capacitor. In order to represent the motion of the sine wave up and down, we have to conceptualize of these vectors. They're all going to be fixed with these directions, but they're all going to be rotating around. So they're going to be spinning. And as they spin, we can find the coordinate that each of them make off of our voltage axis, our vertical axis. We can read the coordinate that the tip of each of these vectors makes, and that will tell us the voltage over that particular piece of the circuit at that given time. So perhaps this right here, the voltage over the resistor is, say, 10 at this exact instant. The voltage over the inductor would be 8, and the voltage over the capacitor would be maybe -6. That's how we would read the voltages. And as they rotate, you could imagine that your V sub r would rotate up and hit a point where it's at some maximum value, and then it's going to rotate past that vertical axis. And the voltage for the inductor will rotate down and cross over the horizontal axis and become negative, and the capacitor will rotate upward. But the most important thing that we can do here is we now have vectors that we can add vector-wise. And so when we add these guys all together using vector rules, then we have a way of combining all of these together, accounting for the fact that they are out of phase with one another. And whoops, I just lost the homework assignment. We have a way of accounting for the fact that they're 90 degrees out of phase with one another and adding them together, and then we can do problems. And my Wiley Plus just crashed. This is horrible timing. Let me pause this recording. I think I can pause it and see if I can figure this out. Oh. All right, we are back. Now, so as I was trying to build up to, now we have vectors that we can combine, the way that we combine vectors together. What that means is that our hit the wall here. That means that our voltage of the capacitor and voltage of the inductor, since they are pointing in opposite directions, we just subtract one from the other. Now, it will be important at some point to talk about when the inductor voltage is bigger versus the capacitor voltage, because one could be bigger than the other. But for now, it suffices to just say we'll presume that the inductor voltage is bigger and subtract the voltage of the capacitor from it. Together, then, we'll get a new vector. And I'm going to flip the screen here, but I have another one. So we will have a resultant vector then that points, say, in this direction, and that vector is going to have a length of VL minus VC because we've subtracted VC from VL. And then we still have our V sub r pointing in the other direction. Now we have two vectors that are at a right angle to each other. So we can add those together quadratically, and we will generate a new vector that looks like this. This will be the net total when you sum them together quadratically. And when you do that, you get what's called the EMF amplitude, so the maximum EMF. In light of this, we can say that our EMF amplitude is equal to the square root of V sub r squared plus V sub L minus V sub C squared. Since we have a squared here, you'll notice that it doesn't actually matter if V sub L or V sub C is bigger in this case. If I divide everything through here by I, if I divide every term by the current, on the right-hand side, what will I be left with? Let's think about this. So I would have V sub r divided by the current. So IR divided by the current is just going to give me an r squared. This is all still going to be under square root. Then I'll have plus V sub L in terms of current was omega Li. So when I divide out the I, I'm just left with an omega L. Then I have minus V sub C. All that would be left there is 1 over omega C. And this whole quantity is still going to be squared. But this is all in one circuit. Now on the other side, we've divided out the current from the maximum EMF. So what are we going to be left with there? Well, we would just be left with something that's like the total resistance of the circuit. And we go ahead and call this impedance. We give it a big capital Z. This is called the impedance for the circuit. And it's a way of describing all of the components, all of the circuitry that's involved there. Omega would be whatever the driving frequency is. So we're going to use impedance in just a second. The one other thing that I want to mention is that we also have this angle here, which is called phi. This is the phase angle. And we can do trigonometric geometry, SOHCAHTOA, with this angle phi, the voltage over the resistor, and VL minus VC. So VL minus VC is going to be the opposite side. The voltage over the resistor is going to be the adjacent side, and then the maximum EMF will be the hypotenuse. So in problem number 7, they give us that we have an alternating source RLC circuit. They give us the EMF amplitude, they give us a phase angle. They tell us the potential difference across a capacitor reaches a given maximum value, and they ask for the potential difference across the inductor at that time. So I know that VL minus VC has to be related to my diagram here. I'll go ahead and write that this is for problem number 7. And I also have the EMF. I don't have anything about the resistor, but I do have the phase angle. And I can say this phase angle will be, sine of that angle will be equal to the opposite over the hypotenuse. So I can say that my sine of my phase angle will be equal to VL minus VC over the EMF. And they give me phi. I can plug that in. They give me the EMF amplitude. I can plug that in. And they also give me the voltage over the capacitor. Yes, so when I plug all of that stuff in, I will solve for V sub L and yeah, and get a value right there. Now the actual value that you get out should be negative. I'm just doing this in my head real quick, but I want to make sure. Oh, I don't have a calculator on me. Let's see. Oh, I can just do roughly sine of 30, which would be a half times EMF voltage. So a half of 6 is 3, and then I'm going to add in. Yeah, so what you're going to end up doing is this will give you some positive value for V sub L. This will give you like V sub L is equal to 8 volts or something like that. This is where the fact that the phasors are rotating needs to be taken into account. Since the capacitor is at its maximum positive value, the capacitor is only going to be at its maximum positive value when it's aligned with the positive axis up here. That must mean then that the inductor, since it has to be 180 degrees off, since they have to make a straight line, the inductor voltage has to be lined up with the negative voltage axis down here. So whatever number you get out of this calculation, that's fine. But what you need to keep in mind is that the inductor voltage does need to be negative. The positive versus negative does mean something. And so in order to get the correct answer, you do have to put a negative on it. And if you got it wrong, that might be why you got it wrong. All right, and we have one more problem. They say in an RLC circuit, can the amplitude of the voltage across an inductor be greater than the amplitude of the generator? Let's take a look at these equations that I have right here for that first part. And we're going to particularly look at this first equation. Whoops, this first one right here. What this equation tells us is that the amplitude of the EMF is equal to the quadratic sum of the voltage of the resistor and the inductor voltage minus the capacitor voltage. So what I know is that the EMF definitely has to be bigger than this guy, right? And the EMF definitely has to be bigger than this guy because it's the hypotenuse of a triangle. The hypotenuse has to be bigger. However, since this leg is VL minus VC, you could conceptualize an example where VL and VC are both very, very, very big. And then when we subtract them, we make a version that's small enough to give us a smaller EMF. So it's a weird conceptual question, but it's just testing that you understand that it's actually VL minus VC that go into the calculation of the EMF magnitude. You could absolutely have a bigger voltage magnitude over the inductor or the capacitor. The way that you would get it is you would likely want, I would just, I guess a large omega would do that. Don't hold me to that though. That's just off the top of my head. In part, let me see if they have any notes. No, they just say, okay. In part B of problem number 8, they ask you to have an EMF, amplitude, a resistance, an inductance, a capacitance, and they want you to find the amplitude of the voltage across the inductor at resonance. So again, we are doing a resonance problem for problem 8 part B, and the resonance problem we know will have an omega driving frequency that is equal to 1 over the square root of LC. I know that in order to calculate the voltage over my inductor, B sub L, it's always going to be omega Li. I have written down an equation there to find omega. L is given in the problem. The only thing I then need is the current, and that current is a resonant current. So remember to go back to when we first introduced RLC circuits. At the condition of resonance, the EMF of the battery is equal to the maximum current times the resistance. So that's the last equation that we can use here to solve this problem, is to set our EMF equal to the resistance times I. We know our resistance, we know the EMF amplitude, so we plug those in here to find I, and then you plug I in right there. So again, this is where your frequency will come from. L is given, I will come from that third equation listed, and then you can plug an L and find the voltage. And that will do it for this week. Again, this is some pretty brain-melting stuff, I think, especially with the phasor diagrams. That's probably new math for a lot of you. So if it is not 100% clicking, don't worry, you're right where you're supposed to be. You're doing great. And just another reminder, you do not have to take a quiz on this. So if you can get the homework done, cool. If you can study some of it, at least maybe the LC, RC circuit stuff, maybe the conditions around resonance would be helpful. That would be what I would recommend studying, and you'll see some examples on old exams that you may be able to get a point or two on them. But that's going to be it for this week. Thanks everybody for tuning in, and have a good week, and see you soon.